Welcome everyone to this talk by Arun Majumdar. Professor Majumdar is the J. Precourt Provostial Chair Professor at Stanford University, a faculty member in the departments of Mechanical Engineering and Material Science Engineering, and a senior fellow and former director of the Precourt Institute for Energy. By the way, I'm Julio Tino. I'm the Dean of the McCormick School of Engineering. And at Northwestern, we are keenly aware of the challenges involving energy, climate, sustainability. In the past year, we have seen results of research in this area coming from many disciplines: civil and environmental, industrial, electrical and computer engineering, synthetic biology also, just to name a few. And that's not surprising. This is a vital issue that affects each of our lives. The title of Professor Majumdar's talk says it all. Energy, climate, and sustainability are the defining issue of the 21st century. I'm putting the word "are" in there. But in fact, is the defining issue of the 21st century. In the last century, innovations brought remarkable improvements in our quality of life, in medicine, communications, computing, just to name a few. But because almost everything is largely based on fossil fuels, we know that growth is unsustainable. So how to make the shift towards a sustainable economy is an urgent need, yet is a very delicate situation. Arun has thought deeply about this, and he has held positions that influence policy in this space. In 2009, Professor Majumdar was nominated by President Obama and confirmed by the Senate to become the founding director of the Advanced Research Project Agency, Energy, or ARPA-E. And he was the senior advisor to the Secretary of Energy, Dr. Steven Chu. And after leaving Washington, and before joining Stanford, Arun was the vice president for energy at Google. So he's a member of the National Academy of Engineering, the National Academy of Sciences, and the American Academy of Arts and Sciences. He received his bachelor's degree in mechanical engineering from IIT Bombay, and his PhD from the University of California, Berkeley. Following his talk, there will be a panel discussion. So as you listen, I would encourage all of you to submit questions in the chat at the bottom of your screens. Arun, the audience is yours.
Thank you, Dino Tino. Thank you for inviting me and giving me the opportunity to speak to the Northwestern audience. Let me put up my slides. I'm assuming you can see all of this now? Great. Yeah, again, thank you for the introduction, and very warm introduction. Energy, climate, sustainability, the defining issue. Let me start by addressing the students. I wish I was an undergraduate student now, a freshman, because I would have then many decades more to live than I have today. Because this generation of students who are coming in as undergraduates have the opportunity to become the greatest generation of the 21st century. And let me explain that by first starting with a little bit of history. Why are we in a place where we are today? How did we get here? Because it's very important to know that history to really create a roadmap for the future and for this generation to be the greatest generation of the 21st century. I'm going to first start by showing you the population history, because at the end of the day, it's about us. I call this the human tsunami. The world has never seen not only so many people on Earth, but the rate of growth of people have been so fast that the Earth has not been able to adjust, because on geologic timescales, things take time. Nothing changes this quickly. Yet we have this amazing growth in human population with a few bumps in the middle because of pandemics. They didn't have the technology of vaccines at that time, so lots of millions of people died. Today we have that. Nevertheless, the sharp rise, the human tsunami, which is now tapering off, and by the end of this century, we will have about 11 billion people. Today, it's about close to 8 billion people. So another China plus India together will be added to the world. That's the world that that our students are going to inherit. So that's one tsunami. The second one is I call the human consumption tsunami. The GDP per capita GDP, not just with the population, per capita GDP has gone up exponentially. And that's due to all the things we consume. And that has gone because of the productivity, the way we count things. And if you multiply that with the population, it is the total global GDP, and you can see the magnitude of this tsunami. Now, if you go back in history, the idea of GDP was introduced in a lexicon by Simon Kuznets, who got the Nobel Prize in economics. This is right after the Great Depression. And he warned the use of GDP to measure human welfare. And yet, that's exactly how we do it today in terms of the economic growth of a country, of a business, of nations, of regions. And because of that, we are feeding into the consumption. That's a human consumption tsunami. And of course, that fueling that is the energy consumption tsunami. And I'm only showing you the last 210, 20 years or so. And without the use of energy, none of that would have happened. And I'm showing you my own personal ancestry out here. My grandparents were born at the turn of the 19th century. My parents were born in the early part of the last century. I was born in the 1960s. My children were born in the 90s. In a matter of 4 generations, compared to 10,000 years before, matter of 4 generations, we've created the energy consumption tsunami. And 80% of this is the primary energy is fueled by fossil sources. And I put Sadi Carnot out there because 90% of the energy used today is via heat. And so this is the state of affairs today. And that's what we have inherited. That is the history, frankly, of the 20th century. And we are today looking at things where we have to face and somehow turn this around. But this is, don't get me wrong, this has amazingly changed the course of history and our quality of life. If you look at how our ancestors, my grandparents and great-grandparents lived, they lived like that, agrarian society. And they used to have farms and livestock, and they used to move by animal power. And that has completely changed. And now we have well-lit and air-conditioned homes. We can watch TV, look at Usain Bolt run 200 meters. We have healthcare. Our life expectancy has gone up by a factor of 2. We have information on our fingertips. We can go to the grocery stores with 100 horses in our car, and we can travel across the world with 100,000 horses in a matter of a day that would have taken months before. We're not going backwards to the agrarian society. So this is here to stay. But this obviously has consequences. This is what we call the Industrial Revolution, and I call it horsepower to horsepower. That's what we have done. And the arteries and veins of any modern economy is the energy distribution and delivery infrastructure. We have the Tesla Edison grid architecture, which was never designed for solar and wind, but that's what we have inherited. And we have the massive oil distribution using shipping or pipelines. And these are the arteries and veins of any modern economy. Without that, we won't be doing what we won't have the quality of life. We would be back in the agrarian society, and we're not going backwards. But this has consequences. I won't spend too much time on this. The global average temperature rise is rising and going up because of the carbon dioxide emissions due to burning of fossil fuels. And we have gone up by 1.2 degrees global average temperature rise from the pre-industrial levels. Now that may seem, 1.2 degrees, but it has not been uniform. If you go to the poles in the Arctic, the ice is melting. The sea ice extent has gone down dramatically in the Arctic, and the air temperature is not 1.2 degrees, it's like 3 or 4 degrees or 3 degrees. The air temperature has gone up. So the poles are warming faster. And it's not just in the Arctic. The land ice in the Antarctic is going down with thousands of gigatons. And at some point, this is going to affect all of us. But if you think that this is only in the poles, think again. I'm going to show you data on summer temperatures. As we know, some summers are hotter, some summers are colder. And if you plot them together, you find that this is the distribution over time. And if you start in the 50s and 60s, you find that this distribution more recently is now, it used to fluctuate. Some summers are hotter and colder. And at the x-axis is the normalization due to standard deviation. And now we are reaching this tail of the distribution, which is the tail is not Gaussian. It's got a long tail. And the tail of the distribution is reaching probabilities of 4 or 5 sigma at a factor of 10 higher than before. And it is not surprising thereby that the all-time high temperatures ever recorded in all places around the world happen only in the last few years. And so this is where we are today. So here's a pop quiz, and I'm going to throw you some numbers, and I want you to think about the units of the numbers and what they mean. There's no grading out here, so all the students, don't worry about it. Everyone's going to pass this. The first number is 1. And the unit is degrees Celsius. It's 1.2 degrees Celsius, but let's say you round it off to 1. This is the global average temperature rise, and we are now seeing the extreme weather, climate-induced weather events that are happening. The second number is 2. This is 2 degrees Celsius. This is what the world had agreed upon in Paris. And now, thankfully, we have gone back to that, because if 1 degree is bad, 2 degrees is really bad. The third number is 800. This is not 800 degrees Celsius. This is not Venus. The 800 is the following. If we are to keep the temperatures, global average temperature rise below 2 degrees, you have 800 billion tons of CO2 budget still left globally. 800 billion tons, 800 gigatons. The fourth number is 40. This is the rate of emissions per year. 40 gigatons of CO2 per year. Just as a reference, just to get an idea of what a gigaton means, if you add up the weight of all 8 billion people on this earth, all 8 billion human beings, if you add up the weight, it adds up to about 0.6 gigatons. And we're emitting 40 gigatons of CO2 per year. And the last number is 20. And that is really the ratio. We have really 20 years left to address this. And so that's the urgency of the issue. It's not just the scale, it is also the urgency. We have to address it in the next 20 years. which is why I started off by saying the generation that is going into freshman and sophomore, they have the opportunity to become the greatest generation of this century. So where are these CO2 emissions coming from? Globally, electricity and heat that we think of as the majority is only 25%. Industry, which is mostly cement, steel, and petrochemicals, is 21%. Transportation is 14%. Agriculture, how we grow food and other forestry, is 24%. It's almost equal to the electricity and heat production. So the reason I say this as a defining challenges of the 21st century, because it is not just the electricity side. It is electricity, it's construction, it's transportation, it's what we eat and what we burn. And I would propose the following. Whatever 10 billion people consume will produce a gigaton scale CO2 impact. This is electricity, heating and cooling, transportation, food, textile has been projected to be 10% of the emissions, water, steel, cement, information. If we do nothing about the energy efficiency of computing, this is going to skyrocket, and so on and so forth. So what I'm basically saying is that if we have to turn the ship and reduce the emissions, it will basically affect every aspect, almost every aspect of our economy. That is the shift that is necessary today in this 21st century. And the next decade or 2 decades are probably the most important ones. Now that's scary, that's worrisome. Is there any good news? And the answer is yes. There's some energy breakthroughs that have happened. One that may surprise people, I'll mention this, is unconventional gas. And that's a temporary solution because it is pushing away coal, which is double the emissions. As long as the methane emissions, the leakage of the methane is low. The second is renewable electricity. For the first time in history, renewable electricity is the cheapest way to produce electricity at scale, at the terawatt hour scale. And these yellow bubbles, the yellow circles, are the cost of solar. The blue circles are cost of wind. And the dashed line, black line, is the cost of electricity production from natural gas. So we're finding that natural gas is not the cheapest way to produce electricity, but solar and wind are, even though they're intermittent. And the third breakthrough is lithium-ion batteries. And that cost has come down by a factor of about 8 in the last decade. And it will soon, in the next few years, reach $100 a kilowatt hour. Why is that important? Because at $100 a kilowatt hour, the range of an electric vehicle and the cost of an electric vehicle are competitive with gasoline cars. And then you would ask the question, why would anyone buy a gasoline car if you have the charging stations in the right places? This is why it's not surprising to many that it took a little while, though, for GM to announce that they will be all electric beyond 2035. And if you look at at least in the stock market, the market cap of Tesla now is more than GM plus Ford plus Chrysler put together. Now, you can argue whether that's accurate or not, but nevertheless, you can see the scale and the views that people have of electric vehicles. This is the good news. But if you think this is enough, this is certainly not enough. We need much more. And I'll tell you what we not have. This is where science and engineering really comes in. We need to reduce the cost of grid scale storage by a factor of 10 lower than lithium-ion batteries. Our nuclear power, which is the largest carbon-free electricity, is too expensive. We need to reduce that cost by a factor of 2. Refrigerants have a global warming potential 2,000 to 3,000 times that of CO2, and it's going to be phased out. These refrigerants that were agreed upon by the Montreal Protocol will be phased out. We don't have a drop-in solution today. It's very important to have energy efficiency, but at low cost. because otherwise it does not scale. Decarbonizing industrial heat is going to be one of the most important, most difficult ones in making steel, cement, and petrochemicals. Hydrogen has been touted to be one of the solutions, but hydrogen needs to be carbon-free and inexpensive. And of course, food and agriculture. And we need a massive global carbon management at scale where we directly capture CO2 from the atmosphere and store it in the ground, because without negative emissions, we're not going to get there. That's the scale of the problem. Just a few ideas of even grid scale storage. If you increase the penetration of renewables on the grid, we need more and more hours of storage. I think that's pretty obvious. But these will be used only about 10 or 15 times a year. So the capital cost of storage has to go down for those kinds of storage. Lithium-ion batteries here today, the minimum cost, the bill of materials of lithium-ion battery is about $50, $60 a kilowatt hour. Pumped hydro and compressed air is here. It's about $20 a kilowatt hour. And we need to be here. And we really don't have any solution. ARPA-E is funding some projects and programs in that. And we really need to be there. And we really don't have a solution. I'll briefly talk about carbon capture. This is, if you are to reduce CO2 emissions and do negative emissions from the atmosphere, we need CO2 capture. And these are now doing sorbents, which are typically amines. People are now making metal organic frameworks, which is wonderful. But this needs to scale up to the gigaton scale. And that cost has to come down. And hopefully, with innovations and science and engineering, the cost will come down. Today, with coal-fired power plants, with 15% concentration of CO2, the cost is about $60 to $70 a ton. And gas-fired power plant with half the emissions, it's about 80 to 90. And for direct air capture, it's 500 to 600. This is untenable. We cannot do that when it's so expensive. So you need research to bring these costs down. And hopefully we can bring them down to the point without violating the second law of thermodynamics, mind you, but down to the point to about, for direct air capture, below $100 a ton, and for point sources, about $10 to $20 a ton. If you can do that, this would be major impact on managing carbon dioxide. What we grow and eat, if you recall, food and agriculture is 24%. A lot of that has to do with meat. For every 100 grams of protein that we eat from, let's say, beef, we emit 25 kilograms of CO2. So for every 100 grams is almost driving, 60 miles of, for every kilogram of meat, beef, it's driving about 60 miles in your gasoline car. That's the equivalent. And there are better ways to do this. Now there are innovations in the food industry that are plant-based meat, which I think is worth looking at. But there are other ways. So this is now, we're appealing to personal choices that people make, which will have a big difference on the carbon emissions. And that is because in many other parts of the world, the meat consumption is increasing dramatically. And this will have consequences on carbon emissions. So we are at a point that it reminds me of a book that I read of Andy Grove, who's the famous CEO of Intel. And his book is called Only the Paranoid Survive. And it's important to make a note of this, because in his book, he described a concept called a strategic inflection point. And he described it this way. This is the point in the life of a business or an industry, or in our case, the world, when its fundamentals are about to change. The change can mean an opportunity to rise to new heights, but it may just as likely signal the beginning of the end. And so we are at one of those strategic inflection points caused by a variety of reasons. And the question is, can we change? Because if you don't, the consequences are dire, but we have to change, and change is important. But it's also important to note that going backwards in the 20th century and looking at the data from there is not a recipe for future success, because that's what got us here. So how do we think about the future? And let me just point out a few ideas. The way to think about the future, because you can't go backwards, there are no lessons in the past, because this is new to everyone. It is important to experiment with new ideas. It's important to look for new solutions. Innovation is important. It's important to look for, if you're doing a business, some first adopters, leveraging something in another field and bringing it into energy and climate and sustainability, looking for new markets. This is the time to experiment. This is the time to take calculated risks. Fail quickly if you need to, but learn from not only your failures, but others' failures. Keep your eyes and ears open. Don't repeat others' mistakes. It's important to be flexible and agile. Your previous competitors could become your partners. This is for the business community. And your previous partners could become your competitors. Things are shifting. It's important not only to look at startups, which we have plenty around here, and there are many around Northwestern as well, but it's very important for scale up. It's important to look at the vision, not just the short term, but the long-term vision, because this is going to take time and this is hard, and execution of those ideas. And of course, there's no question, we need talent, we need education, and we need money, we need capital. What I'm describing to you is what's the innovation ecosystem, and that's what we need. So I'll say a little bit about Stanford. We looked at this, the whole energy sustainability and climate issue, and we have decided that we will start a new school at Stanford. And this was announced last year. And it's important to note that we have now 7 schools. All 7 schools were started in the first 63 years, and we haven't started a school in the last 73 years. That's the life of Stanford. And we decided to do this to create what we're calling the 21st century school to address the 21st century problems. And this school, even though we're putting climate and sustainability in one school, the porosity of this school to the rest of the university is going to be extremely important. How we structure it, how we operate it, and what kind of people go in, and what kind of DNA is created is going to be extremely important. And how we engage with the rest of the world, this cannot be done in isolation. This has to be done in a coalition and partnership. And how that happens is going to be very, very critical. And this is an experiment that we're going to try, but we're determined to go in this direction. Let me end with a quote from Martin Luther King. We're now faced with the fact that tomorrow is today. We're confronted with the fierce urgency of now. In this unfolding conundrum of life and history, there is such a thing as being too late. Thank you so much.
So thank you very much, Professor Majumdar. That was a really great talk. Now I'd like to introduce the panel portion. I'm Bill Miller, a professor of chemical and biological engineering, and I direct the Center for Engineering Sustainability and Resilience. And with me will be Jennifer Dunn, who co-directs the center with me and is also the director of research at NAES, and also Michael Wozlewski, who is the executive director of the Institute for Sustainability and Energy at Northwestern. And we would love you to put your questions into the Q&A for Professor Majumdar and the rest of the panel. So I'd like to move to that now. And Jennifer Dunn will be coming back to us with the questions.
Great, thanks, Bill. While all of our attendees are entering their questions, I'll just get us started with a question around the challenges that you discussed and their kind of severity and their just how multifaceted they are. How do you see balancing the need for immediate action with the need for fundamental research as we look towards developing solutions?
That's a great question. It's not either or. I think sometimes we fall in the trap of either this or that. I call it the tyranny of or, as opposed to the harmony of and. You need both. We do need to act now. And we do need to look at how to decarbonize, whether it is introduction of renewables. There's a lot of focus on that right now. There's a $2 trillion infrastructure proposal out there in Washington. And that is really to create the infrastructure for clean energy, because we need to do that. We absolutely need to start that now. The infrastructure is very important. One of the lessons we learned from COVID is that it is one thing to have a quantum leap in technology, in this case, mRNA vaccines. It's an entirely different challenge to deliver them and vaccinate people. So even though we may have a quantum leap in storage technology, for example, availing of the opportunity to use the storage technology needs infrastructure, needs transmission lines, or need other supply chains. So I think it's very important to build the supply chains and the infrastructure starting now, so that when the technologies keep improving, we can slide them in place and use them when we need to. So it's not an either or, but it's an and. But you need both. You need the R&D, because this is not going to be solved in 10 or 20 years, even though people are saying that in 20 years we'll be net zero. Well, yes, but there's a risk that you may not quite get there. This is a century-long issue that we need to address, because it is global. It is not just the United States.
So maybe I could add one comment and maybe add another question. I guess one of the big challenges is ensuring that we don't lock into other technologies. One of the real criticisms of carbon offsets is that it can make it easy for people to then pay off for their credits and then lock into a new technology like another coal-fired, maybe a petroleum-powered power plant that would then be used for another 20 or 30 years. So I guess the question is, how do we make sure that early on we don't make any more investments that are going to be hanging out a long time with large CO2 emissions?
Right. So, we can't stop using fossil fuel today or tomorrow. So it's a question of really, we are really trying to redesign the plane, change the wings and the engine and the fuselage, and get a new plane without crashing it. That's the challenge. And it's not going to be easy. I mean, there's no question. So we will have to use some fossil fuel for the next 20 years. The question is not the fossil fuel, it's the carbon burden. And which is why I think it's so important to figure out how to manage CO2 at scale, at the gigaton scale. Because putting everything on the electricity basket is actually risky. Because when we're talking about energy, it is so fundamental in terms of infrastructure to the whole economy that you got to balance this with not only economic growth and the environment, but the national security aspect. So if you take if you put everything electric and someone hacks into the grid and collapses it, then you don't have any other way to, operate. And so it's very important to have redundancy in the system. And so use of some clean fuel and in a clean way, whether you manage the carbon is very important. And so I think we have to look at it and hedge our bets on that.
Arun, you made a point about the really huge importance of storage with any renewable technology. Going beyond lithium batteries, what technologies do you think are favored at this point? I mean, are we going once again toward using hydrogen as a storable fuel, or is there something else on the horizon?
Hydrogen is certainly one of the options, but it has to be stored at scale, not at small scale, but large scale, whether it's geologic storage or not. Electrolyzer costs have to come down quite dramatically. But there are other storage. I mean, there are electrochemistries based on iron and sulfur, which are, the oil and gas companies will pay you to take away the sulfur, right? So if you can use that reducing agent with a redox pair with iron, let's say, then you have a possibility, and people are trying that right now. Believe it or not, if you look at the economics of it, taking electricity and doing I²R heating to very high temperatures, and then running a turbine, which is thermal storage and then electricity generation with about 50% efficiency round trip, 40 to 50%, that turns out to be really inexpensive. And that is because when you heat things, you use every atom that contributes to heat capacity. Whereas when you have electrochemical storage, there are parasitic other materials that you need that is not contributing to the actual storage. And so turns out that thermal storage and heat production, even paying the penalty of Carnot, turns out to be a fairly cost-effective way to do it. So there are different approaches when you're trying to do this at scale.
Thank you. I'm going to turn to a question from our audience, and I think you're particularly relevant to address this question, given your experience in different sectors, government, industry, academia. What do you see as the greatest points of friction in convincing a turnaround in the business community and in industry? Is it viable or likely to happen, and any indications that it might?
That's a great question. It's interesting that I wish I was, in 2009, this had happened when I was in the government, but it's happening now, which is great. More than 25%, about 30% of the Fortune 500 companies have made net zero commitments. If you add up the annual revenue of these 30%, 25 to 30% of the Fortune 500 companies, that's more than $10 trillion, about $12 trillion per year. That's more than half the US GDP per year. Okay, so this is a big thing. You're finding Wall Street, the big asset managers and all are saying that that we want to invest in companies that have a long-term view on carbon. And so you're finding that the business community is lining up in this direction. What is really needed now is the environment created by the government with the right policies, which are long-term predictable signals. The government needs to give long-term predictable signals to decarbonize so that the industry can respond to it and plan out the investment portfolio. These are resource allocation decisions that boards and CEOs will have to make. But if your policy, the government policy is fluctuating and there's uncertainty, as we have seen in the United States, the business community will say, wait a minute, I cannot go in there because I have shareholders to care about. I worry about the earth, but I do have shareholders. So that alignment of the government and business is going to be absolutely critical.
Any other panelists care to comment? Okay, so along this theme of multiple things needing to come together, Zahir asks whether you think we will see synergies in decarbonization efforts. So the sectors that you described at the outset of your talk are all interlinked. For example, Zahir says, do you think that the growth of electric and hydrogen vehicles could reduce both, for example, transportation and agricultural emissions because of cleaner farming equipment and other synergies that you foresee?
Well, actually, on the agricultural side, if you can somehow decarbonize hydrogen, it's a big deal because agriculture needs fertilizers. Fertilizers come from Haber-Bosch process. And today, that hydrogen comes from natural gas in steam methane reforming, and that has carbon emissions. If you could figure out a way to cost-effectively produce hydrogen that does not have carbon emissions, you have made a major dent in the agricultural side because your fertilizer will be low carbon. And so I think that in the hydrogen and agriculture, there's a big, strong connection because of the Haber-Bosch process. I think the hydrogen use, it really depends on how you use it, the value of the hydrogen. If you're using it as a reducing agent, which is what is used in the petrochemical industry, whether it's fertilizer or in cracking petrochemicals, long chain hydrocarbons, then the cost of about $1 a kilogram, which is what it is today, is fine. If people have been suggesting that we should use hydrogen as a heating fuel, $1 a kilogram is about $7.50 per million BTU. And that cannot compete with natural gas at $3 a million BTU, even if you price the carbon. So if you really want to look at hydrogen, and a lot of people talk about hydrogen economy, and we are writing an op-ed right now, it really depends on how you use the hydrogen and the value it provides. And if you want to use it as a heating fuel, boy, that has to be 50 cents a kilogram. And today we have no way to make carbon-free hydrogen at 50 cents a kilogram, leave alone at $1 a kilogram. So this needs some fundamental research to figure out how to produce hydrogen, carbon-free hydrogen, at less than $1 a kilogram. No one has the answer to that.
So you mentioned, the need to decrease the cost of fertilizer. Another approach would be to gradually or rapidly, actually, to a large extent, decrease the amount that's needed by managing farmland better to reduce runoff and also to build soil health, things like cover crops and other processes. And there was another question that I saw as well about sort of reforestation. What are your thoughts on so-called nature-based solutions as opposed to the others? How big a chunk of the pie do you think that would be?
That's a great question. I mean, to your point about fertilizer, there are now technologies that are being commercialized right now of ways to use bio approaches to fix nitrogen in the soil. And this is one of the hardest problems, is how do you break the triple bond of nitrogen and do it at scale and make nitrates that can be put in the soil. This is going on as we speak. So absolutely, there are other ways of addressing the fertilizer problem as well. What was the second part of your question, Bill?
Yeah, the idea of, say, reforestation or afforestation as a means of, as opposed to, say, carbon capture and storage. In other words, biological capture as opposed to geological capture. So
there's a wonderful paper that came out in PNAS in 2017, I believe, called Natural Climate Solutions. The first author is Griscom, and I would encourage you to take a look at it. And they've laid out all the possibilities of natural climate solution. And what turns out to be one of the lowest hanging fruits, interesting enough, is to increase food productivity. Because if you increase food productivity per acre of land, you don't have to do deforestation. And that goes back to the fertilizer issue, but even more, I think there's an opportunity for a green revolution using the gene editing techniques and all. And yes, there are social issues concerning gene editing and how it can be used for agriculture. But nevertheless, I'm a product, my generation growing up in India is a product of the first green revolution with Norman Borlaug of short strains of wheat. There is a need for another green revolution because not only the population going up and the food that is needed, but also to increase food productivity and use that mechanism to store carbon in the soil. That needs to be done to address climate issues. So yes, natural climate solutions, absolutely. I think there are a lot of discussions going on. We have had like 2 workshops now at Stanford on this issue. It is not just enough to do forestation because the photosynthetic efficiency is so low that you need a lot of land, because the rate of absorption is important. It has to be on the gigatons per year. It's not just the capacity of forestation, it's the rate. And to do that at the right rate, you need a lot of land. And I think that's the critical issue, is that should we bank only on that? And the people who do natural climate solution, they said, please don't bank only on this one, because there are uncertainties involved. We don't know the full carbon cycle completely, and we need a lot of land. So food productivity, absolutely key.
So one other question I saw that sort of relates to this is, food productivity is needed because of the increase in population. What are thoughts on, what is the maximum sustainable population? We've had different theories over time, but what are your thoughts on population rise? Is that something we can afford?
Yeah, some of the theories came out of Stanford that, the world cannot sustain so many people because there's not enough food. That was thrown around. What they did not account for was technology improving food productivity, and now we have sometimes abundance of food, right? So I'm a big believer, and not surprising, that technology has to play a role out here. And this is where science and engineering has to come together to create these breakthroughs in technology to be able to support the population. So, trying to control population is a socio-cultural issue, and I won't even go there. Let's take the boundary condition, or the initial condition, that there is going to be a population of about 11 billion people. The question is, what do we do now to support them and to make sure that they have the right quality of life? And that's the question. And then the question is, what technology is needed to do that without carbon emissions? And that's what I would, that's what I would do. But technology will absolutely, without the technology, we're not going to be able to solve this problem.
Thank you. We have a question from a future Stanford doctoral student who's looking to do research around energy. So her question is, looking more globally, what is the strategy for not just the advancement of sustainability in world powers, but also developing nations who might lack the resources, wealth, and infrastructure to maybe develop some of these solutions, but would be disproportionately impacted by climate change? And what role should nations like the United States play in addressing those inequities?
That's a great question, because it has so many dimensions to it, including geopolitics, finance, environmental justice, equity, global equity, etc. And I think it's important for us to recognize that the lifetime of CO2 molecules in the atmosphere is several hundred years, which means the reason that we have global warming is not just due to the emissions that we are over the last few years, but it's the cumulative, it's the integral under the curve. And a large fraction of that came from the United States and developed countries. And so if that's the case, there is a responsibility of the developed countries to decarbonize as quickly as possible, to enable and empower the other countries do not have where the quality of life or the human development index is too low. And I don't use GDP. I use human development index is low. Then they need to improve the quality of life with education, health, water, clean water. They need to go up the human development index in a curve, and that will require energy. So they have to grow. And there are other countries that haven't even started, mostly in Africa, and they have the opportunity to leapfrog. So the rest of the world is not uniform. There's China, where the infrastructure has pretty much already been developed, and they will have to now, displace the coal and put renewables. That's what they'll have to do. In India, the energy demand is going to be so high because of the economic growth that by 2040, the demand is going to be 3x the electrical power of today. Okay, so that infrastructure has not yet been built. But it's not going to be a completely different technology. It's still today's technology, but the infrastructure of transmission lines, wind, solar, nuclear is yet to be built. On the African side, which is where the most population growth is going to be, it's a very different story because they have the opportunity to leapfrog into new technology. And so I think the world is not flat in this case, and the response, the solutions are different for different parts of the world.
And certainly, I think some of us are very keenly aware that some of our primary solutions, like lithium-ion batteries, are dependent on global supply chains. And the popular press has covered a lot of the effect that some of our shipping of solutions is having on these other nations, like Chile or Democratic Republic of Congo. So I think, in my opinion, we also need to be mindful of, as we seek solutions, the impacts that our solutions can have on others.
Absolutely, yeah. I think Tino has a question.
Oh.
You want to? I think you're muted. You're muted.
Yeah, I ask you this because I work a little bit on this. So what's your view on these things that are easy to grasp? There was a paper written APS maybe 15 years ago on how big they have to be to.
Yeah, I was part of the APS committee that wrote the report. Yeah, Climeworks and carbon capture, this is using amines supported on solid supported amines. And I think it's, first of all, I would say it's very important to get it started. The cost is still high. It's about $400 to $500 a ton of CO2, but you got to learn by doing. And maybe you change the amine to a secondary amine or tertiary amine, whatever, maybe MOFs, but you need a system and a test bed to actually get it started. If you look at I didn't show those slides. If you look at any direct air capture technology today, they are a factor of 20 away from the thermodynamic limit. And it's not difficult to calculate thermodynamic, it's just entropy of mixing. That's the minimum free energy. That's the minimum work that you need. So if you take that and where things are today in the actual real world, there's a factor of 20. Now, you do not want to be at the thermodynamic limit because there's no kinetics then. So if you can get to about 4 or 5 times the thermodynamic limit, which is still a factor of 4 or 5 better than today's technology, that's where the goal ought to be. And most of the energy consumption, if you really do accounting, is in the heat that is used to desorb. And if there are ways to, again, manage that heat in a better way or find other ways of dissociation of the CO2 to any sorbent, whether it's amine-based or whether it's carbonate-based, I think that's the key to really bringing down the energy penalty, energy intensity, and thereby the cost.
Okay.
Great. I think there's a really nice question for the students in the audience. You mentioned that now is a great time to be starting college and having the opportunity to be the greatest generation of the 21st century. In the context of energy and sustainability, where is the need most acute for young talent today, be it engineering policy, techno-economic analysis, or other areas?
Let me answer this in a different way. The need is so big. You can remain in, chemical engineering, or you can go into economics, or you can go into law, or you can go into business school, and you'll find a place. Because we're talking about a shift in the whole economy. This is not a small thing, and this is going to be hard. It will, and the greatest generation in the 20th century came out of the Great Depression, which was a global event, and World War II. It was a global event. This is a global event of that magnitude. And no matter which direction you go, you will be affected by it and you will have a place in it. So my suggestion to the students is stay in school, get an education, graduate, keep an eye out for opportunities in this area to serve, and do something about it.
Thank you. So bringing this whole shift in the economy concept, there's a lot of discussion today around the circular economy. And what are your thoughts on the circular economy and its potential contribution to sustainability and reducing greenhouse gas emissions?
Critically important. That is a dramatic shift from the 20th century economy, which was a one-way traffic. You get things out, you burn them, or you make something and just throw them away. So getting the circular economy going is great. And I'll just give you an example. We're also excited about electric vehicles and lithium-ion batteries. At some point, we'll have so many lithium-ion batteries that we don't know what to do with it. And so figuring out how to extract the minerals from existing lithium-ion battery, which there are technologies, a lot of focus on that. I know in Oregon National Lab in Northwestern and many other places, and there are companies that are starting, I mean, so that you don't have to go to Congo for copper mines to figure out where to get cobalt from, et cetera. That's going to be really, really important, and there'll be value for it. And so that's just one example. What I really worry about is textiles. When I was a kid growing up in India, I basically had 2 shirts or 3 shirts. My parents didn't have much money, and we used to wash them and use them. Now, if I look at my closet, I don't know how many shirts I have that I don't wear. And this is not just my story. I think everyone can relate to that. And what has happened, if you look at the data, that the number of times a new clothing is used before it's thrown away has gone down. And so this is worrisome because the impact of the textile supply chain is about, by 2040 or so, it's expected to be at 10% of the economy. And most of the growth is in the polymer-based polyester. And so this is a concern. So I think we need to figure these things out as well. Yeah. In a circular economy. How do you reuse the polymers to make clothing again? And today we just burn them or put them in landfills.
Okay, so I think we are reaching the ending here. So this seminar, this talk was sponsored by ISEN, which is the Institute for Sustainability and Energy, and the Companion Center of Engineering Sustainability and Resilience. But when you answer the question of where should I go, what should I study, you said, doesn't matter what you study, just there's a place for it. So this seminar could have been sponsored by everybody in Northwestern, because everybody has a role to play in this. But this was a masterful presentation of the big things occurring in this space. And we are so happy that you were able to do this for us, Arun. Thank you so much.
Thank you. Thank you very much.
To everybody for attending, and thank you to the panelists. Look forward to connecting with you again at some point. Bye-bye.
Thank you so much. All right. Take care.
Thank you, Arun.
Thank you so much.